Okay, good afternoon, everyone. I Kaushik Dhola, convener of this STTP. I warmly welcome our expert, Dr. Sabha Raj Arya, and I welcome Dr. N.R. Patel, convener of this STTP. Let me introduce our expert. Dr. Sabha Raj Arya received his bachelor degree in electrical engineering from Government Engineering College, Jabalpur, Madhya Pradesh in 2002 and master degree in electrical engineering with specialization in power electronics and
सब फोन करता हूँ दोपहर ढाई बजे
ASIC, designed from
हाँ मैं लिखूंगा
MNNIT,
आप लिखो
Allahabad, Uttar Pradesh in 2004. He received his PhD degree on electrical power quality in electrical engineering from IIT Delhi in 2014. He is currently working as an associate professor in electrical engineering department SVNIT, Surat, Gujarat. He is recipient of Young Engineer Award from Indian National Academy of Engineering and many other prestigious awards. He has prominent areas of research are power quality, power electronics, electrical vehicle technology, optimization algorithm, distributed power generation, smart grid technology, and many more. He is associate member of Institution of Engineer India and senior member of IEEE. He has published around 70 research papers in national and international journals and 63 research papers in national and international conferences. Today, he is going to deliver an expert talk on custom power devices and its application. Now, I would like to hand over this session Dr. Arya sir. Thank you, sir.
Thank you, sir, for nice introduction. Now, thank you, Nikul sir. Thank you, sir. And today we are going to discuss.
Thank you very much.
So today I am going to describe about the again some application and as well as the design and control. And in that case, we will take custom power devices, and that will come in the category of composition type of maybe fact device you can say like that. So in that regard, we are going to start our talk in the area custom power devices. Okay? Okay, now now our slide is coming, sir.
Yes, sir.
Yes.
Definitely.
Okay. Now we are going to start. So in this case, today means first we will discuss something basic only. Here how our district com is going to work. After that, what are some applications? Application means we can apply this device in many cases. All the distributed power generation we can apply. Maybe solar, maybe wind, maybe small hydro, or maybe micro hydro also we can say. Maybe diesel engine. With diesel engine also we can apply. After that, maybe you can say biomass. In that area also we can apply. Means meaning is this one place where we want to get the power. Input is anything you can change. Wind, solar, hydro, anything you can change. At that power we want to utilize for public use. We want to utilize for public application with more effective way. In those applications, this thing is more useful. Again, point are there. This one also we can use in case of vehicle application. Means just like a battery charging application, you can say. Means that converter, whatever voltage converter we are going to use as a filter, that converter also going to work as a battery charger. Means input you can connect from line and output DC link, whatever DC link we want to maintain for composition. From that DC link only we can generate the required battery voltage. Means we can put battery charging in DC link, and by maybe in this place we can design whatever converter you want, DC converter. By that one you can design battery charger, smart battery charger you can say. Means whatever converter we are going to use, that converter is going to work as a battery charging as well as the power filter. Okay, so means many applications. So means due to these so many applications, people are going to work. Many people are going to work in the area of shunt filter only. And still maybe very less paper, maybe not less paper you can say, very less people we have observed in the area of series filter, or maybe you can say DVR, or maybe UPQC. UPQC maybe some people are working, but shunt filter maximum people are working. Yeah, that one application, they have so much application you can say. Maybe vehicle side you can say, maybe you can say distributed power generation you can say, grid connection you can say, grid connected system also we can say. Means whatever solar are there, wind are there, hydro are there, na, by then whatever power you are going to generate, by that power also we can supply to grid also. One application. A second application maybe we can supply to local load. In that case also we have two sections. One is the wind, one is the grid connected system, second on the local load. Local load also we can supply. In that case we want to, final objective is we want to reduce the losses. This is our final objective. Okay. Means finally we want to reduce system losses. Okay. In that regard, I want to discuss something about the basic first. Okay.
Yes,
So
sir,
hello?
Sir, sorry for disturbing. PPT in presenting mode, sir. So in presenting mode, PPT so.
Where?
Yes, sir. PPT जो दिखाई देता है वो अभी स्मॉल साइज है, तो उसका प्रेजेंटिंग शो में कर दो सर. यस सर, यस सर, यस सर, यस सर, फाइन.
Okay.
डेफिनेटली.
Now,
और हाइड,
okay.
यस, इसको हाइड करना है.
Okay.
ओके, नो प्रॉब्लम सर.
Okay. So here basic application is, generally we have two types of problem. Maybe due to load, you are going to have a problem in supply system. Second one, maybe due to supply itself have some problem. So if we are going to see problem due to load, means load is current. Load is going to demand the current, that demand current, whatever current that load is going to demand, in that whatever problems are there, that suppose we want to solve. So for that one you can use this distribution static compensator. Means by using distribution static compensator, we want to eliminate current based power quality problem. Simply you can say like this. Second one, this whole device, maybe again we are going to compare with shunt active filter. People are thinking shunt active filter, and we have two names. We have two names. One name means active filter, second name D-state com. So means here basically there means function wise some difference people have identified. Initially people are telling that active shunt active filter is going to work for compensation of only harmonics. Shunt filter basically people have developed for compensation of only harmonic component. Mean whatever distortion are coming, that one suppose we want to compensate for compensation of distortion only, we have designed shunt active filter. But that shunt active filter later on people have increased their rating, and people have also used for reactive power compensation. Okay, to people before 10 years before, maybe you can say before 2005 or 2004, maybe you can say. In that time, not 4, even in 2002 also, we have received one book that power quality by custom power device by Arvind Ghosh. Before that, maybe you can say. People are telling me we have a shunt active filter. Shunt active filter going to work for reactive power and harmonics. But primary objective is only harmonic compensation. Later on, after 2010, after 2011, I mean after 2007-8, people have again just some modification, and they have increased the more number of functions from that voltage source converter. Okay, meaning of this one is more number of function means if in place of one person or two persons, suppose we are going to get 5-6 persons or more than 3-4 persons, then we have more advantage. Even rating going to increase. If we are going to operate or we are going to compensate all the problems at a time only. At same time, we want to compensate all the problems, means harmonic, reactive power, neutral current, unbalancing. Same time, all problems will not come. Maybe sometime neutral can come, maybe some neutral can be continuous, maybe sometime unbalancing are there, load unbalance, sometime maybe reactive power is there, sometime maybe distortion are there. At a time when 1 or 2 problems will come. So in that cases, this type of system is more useful. If even at is medium rating also. But if you are telling all these problems coming at a time only, same time all problems will come. In that case, we should increase the rating of the power converter. Okay, means D-state com basically people have designed for compensation of reactive power. For compensation of reactive power, people have designed the D-state com. But additional features are harmonic compensation, unbalancing. If load is unbalanced, so this one is going to maintain supply side balance sinusoidal current. This one not going to do anything towards voltage side. This is one thing. Again, if we have 4-wire system, in that case, this whole voltage source converter is going to work as a hello. वो मैडम के पास होगा वो हाँ मैडम के पास होगा हाँ हाँ तो मैं मैडम के पास ही होगा हाँ हाँ ठीक है बना दूंगा हाँ हाँ ओके तो मेरी नेक्स्ट पॉइंट इज current related power quality problem. Okay. Second thing is if we have four wire na 4-wire system. In that case, we want to compensate neutral current. Neutral current means generally at present people are going to use some transformer based connection, delta star, zigzag star, or maybe some other thing. Means suppose primary side you have a delta, or primary side you have a star, or secondary side you can make delta. So third harmonic going to circulate inside the whole delta only. That is also one option. Suppose you want to compensate by passive arrangement. Suppose second case, suppose you want to compensate by active arrangement. That is one more very good option. But in that case, we need controller. Then we need one leg also, one 4-leg converter also. So, but if we have we are knowing we have 5 ampere, 10 ampere neutral current always. In that case, we can put passive compensation more useful. Passive compensation not going to burn. Means we can put 10 kV transformer, 5 kV transformer, put delta star connection, then you can use. Okay, that is one thing. A second thing, maybe you can use zigzag connection. In that case, we are not going to block the harmonic. We are not going to block the neutral current. We are going to compensate the neutral current there. But in case delta star, we are going to block the neutral current, you can say, towards secondary side. Means secondary side, neutral current is going to flow circulate only. Okay, so meaning is this whole device is going to work in 2 modes. One is the PFC mode and ZVR mode. Means we have additional feature here. Means this STTP is going to work for 4 functions. If we have 4-wire system, additional with voltage regulations. Means we are going to achieve the voltage level near to rated value. But main power, but still we have some problem. Due to that one, people are going to use series filter. By that one, we are not going to maintain UPF. We are not able to maintain the UT power factor in supply side. If we are going to operate, this state come in ZVR mode. In that case, always we have some amount of leading power factor. Why we have leading power factor? Due to extra requirement of reactive component to compensate the voltage. Okay. Again, this whole system is going to operate in PWM mode only. Means maybe you can operate frequency not more than 5 to 10 kilohertz. We are not going to make 30 kilohertz, 40 kilohertz. 5 to 10 kilohertz, 10 kilohertz sufficient for turn on the IGBT if converter is going to work as a distate com. Okay. So again, advantage, first this we have discussed. Main advantage, dynamically you can compensate. If our reactive power is high, leading reactive power high, this will supply lagging reactive power. If lagging reactive power is high, this will supply leading reactive power. Dynamically, this converter is going to adjust their property. And capacity for tangent overload, even during low voltage also. Here we have a capacity for tangent overload and very low voltage also. Okay, then you can see this system is going to operate in PFC mode and ZVR mode. In this mode, in case of ZVR mode, source current are slightly leading with the respective voltage because extra leading reactive power is required to regulate the PCC voltage. But in first case, we are going to see what we are going to see? We are going to see UT power factor means angle between supply current and voltage is 0. Angle between supply phase current and supply phase voltage. Again, you can see phase current and phase voltage, not line current phase voltage. Line voltage and phase current, you can see. Means we should see angle between phase current and only phase quantity only, you can see like that. Again, that Again, utilization of this one depend upon the maybe control, what type of control you have used. Topology also you can see how many functions we want, and also getting signal and power circuit element. Okay. So again, point are there. In this case, this whole converter maybe you can convert, you can control in two ways. One is directly you can generate the compensating current. One case directly we can generate compensating current. Where directly you can find out the value of ICA, ICB, ICC. Second case, maybe you can find out the what we can find out fundamental component. Suppose we have one square wave. Do that. From a square wave, suppose you have removed all the distortion, and finally we have got one sine wave. At that sine wave, we are going to assume that this is the ideal condition. Okay, and we are going to assume that supply can teach whatever the sinusoid current we have got now, that is the ideal sine wave. That ideal sine wave we can compare with whatever distorted current are there. If we are going to compare ideal person from distorted person, then you will get some error between ideal and non-ideal. By that error, you can generate the required compensating current. That is the indirect current control. We have two theories. One is the direct control, second was the indirect control. In case of indirect control, we want to generate error. But in case of direct control, directly you can generate the required compensating current. Okay. Clear now? Means here always we are telling why we should generate the reference current, why we should generate reference voltage. That is two way. That is two principles are there. One is the direct compensation. Second one the indirect compensation. In that compensation, we need to generate some reference, or that reference is going to compare with whatever actual value are there. After comparing, you have error. That error is going to, using that error, you want to generate the compensating. That error you can feed to PWM controller, and you can get a gate signal. Finally, you have a compensating current. Okay. Again, in literature, many controllers there. Maybe you can use. Here we have divided whole classification, whole control classification with 3-4 types. Maybe you can say. First, maybe based on their domain. So they have two type only, frequencies and time domain. Again, inside of time domain, again depend upon their circuit structure or maybe their property. So maybe you can say classical, maybe you can say transformation based, you can use some transformation. Third, maybe you can use adaptive control. Fourth, maybe you can use some artificial control, artificial intelligence. Okay. Again, point are there. Inside of this one, again we have some error regulators. So suppose we want to regulate component, the error regulator gains. So to regulate that error regulator gains, we need to develop some algorithm to regulate the error. After regulation of error, reference that sense value going to touch the reference value. But same time, to achieve that one, we need to tune the value of PI controllers, because PI controller work as a error regulator. In that case, how we can decide the value of KPKI? That is also one of the research area we can see in this section. What of section other means custom power devices, or maybe drives area, maybe vehicle area, whatever area there. Na? In all the cases, we have error regulators. So here just for learning purpose only, I have given one basic control, single phase PQ theory. But this is so much old only. Just only by this one we can understand how we can generate the required reference current. Okay. So in this case, if single phase PQ theory is there, you can control, independent control you can use. All three phases independently you can control. All three phases independent we can control. Okay. And high convergence speed, but okay, we can say, we cannot say also. That depends upon the processor. Independent control in all three phases. Structure of this control algorithm based on the basic arithmetic operation. Due to this, its implementation in software and hardware is simple. Again, whatever algorithm we are going to discuss, that one basically based on the mathematical calculation only. We are not going to use any loop. We are not going to use any iteration, we can say, any tuning process, you can say. In that case, whole algorithm is based on the mathematical calculation only. Okay. In that case, maybe implementing is somewhat easy in software and hardware, you can say. This is the one basic circuit diagram. In this basic circuit diagram, what we can say, we have a supply source. In the supply source, maybe what we can say, in the supply source, maybe we have 3-phase 3-wire, or maybe 3-phase 4-wire. After that, always we have some source impedance, ZS. ZS means inside are RS and LS. Again, point are there. Suppose we want to develop some software based some simulation or something, maybe software based some system. In that case, suppose we have a 3-phase supply source. In that, we need to design the source impedance. So again, we can remember based on the L by RSU. See the L by RSU. So maybe you can see what is the value of L by RSU in case of distribution system. And in transmission, what is the in transmission also you can see value of L by RSU. Okay. So in that way, you can design source impedance. Means if we have perfect source, perfect value of source impedance, then you are able to get the required result. Otherwise, the problem will get. Suppose you have put 10 millihenry, 5 millihenry, or some higher value, then some high distortion you will get. If suppose you have removed the source impedance, maybe 0 you have put, you are not going to get any voltage drop. That is major problem. But in actual practice, always we have some value of source impedance. So in a simulation, generally we are going to use X by RSU not less than 10. So based on X, first R you can assume that maybe 0.01, 0.001, 0.005, less than 0.1 you can say. Based on that one, maybe 2 millihenry, 3 millihenry, 2.5 millihenry, you can put the inductor. Okay. Okay. After that, you assume that we have created some load. That load are based on the maybe linear load, maybe non-linear load. Again, linear load means maybe rectifier, maybe some switching type of load, maybe some machine load are there. In case of non-linear load, in case of linear load, maybe we have a inductive load or capacity load with reactive power demand. Okay. In that way, means we can separate out the linear and non-linear loads. Okay. After this, here we have used one delta star connected transformer to compensate the neutral current. So here central line of star connection we can connect to neutral wire. You know, whatever neutral current is there, that neutral current is from load side, whatever neutral current you are going to observe, and supply side, whatever neutral current you are going to observe. After compensation, we have a different value. Means we have a star connection. At midpoint of that star connection, you are going to connect neutral wire. So that current and load neutral. If this system is going to compensate neutral current, so our transformer neutral current and load neutral current both are equal and opposite in phase. If both are equal and opposite in phase, in that time we are going to observe zero neutral current at supply side. Okay, means transformer is going to provide equal and opposite nature of the compensating neutral current. That is meaning. Okay, then since frequency of neutral current how much? 150 hertz, third harmonic only. Okay, and that one is going to circulate inside the delta connected winding. We continue this one, we will circulate only. This will not go anywhere. Okay, so that one is going to circulate and make the losses only finally. Okay. This is one thing. Second point is there. By this one means here many connections are there, not one connection. Just I have told only one connection only. Here you can have more than 10 to 15 connections. In literature, many connections are there. Just maybe you can read also. And also maybe based on, if you are able to find out some new connection, you can develop connection, and also you can test. If that test is going to work very well, then you can use, you can write somewhere paper here and there. Okay. Then after that we have voltage source converter. This voltage source converter is going to compensate reactive power, harmonics, and unbalancing. Again, point are there. How much neutral current will come from load side? This is the main thing. How much neutral current is going to come from load side? If we have a pure, if we have a linear load, simply you can say. Simply linear load means RL load. RL load means simple resistive load plus inductive load. In that case, that is balance also. If balance, in that case, if load is balanced, in that case, we are not going to observe any neutral current in both wire. If load is going to become unbalanced, where some phase 50% load, some may 40%, some may 70%, then you are going to observe unbalancing in whole three-phase load, three-phase section. Now, due to that one, we are going to observe neutral current in both wire. Okay. How much? In normal condition, neutral current equal to how much? Load neutral. Neutral current equal to whatever load current are there, both are equal in normal condition. At normal condition, neutral current and load current both are equal. But if abnormal condition are there, magnitude wise you can say, but frequency is 150 Hz, IL have 150 Hz. If load has 50 Hz frequency. Second case, if we have heavy unbalancing, at that time, maybe neutral current is going to increase up to √3 into IL. In case of unbalanced system, neutral current is going to increase up to how much? Up to 73% each time, can say. Okay. In that case, means IL is going to increase √3 into ILN. √3 into IL. Again, this is one thing. Second main point is there. At what condition this circuit is going to work as a compensator? At what condition this circuit is going to work as a compensator? Okay. And what we can say? Anyone? At what condition this circuit is going to, this voltage source converter is going to work as a compensator? Anyone can tell? Hello? Hello?
Yes, sir.
Anyone?
Yes, sir.
At what condition?
If any questions from the participants, I will definitely interrupt you and ask the questions.
Okay.
It is a smoothly coordinate right now. Presentation is going on. So, shall you continue, sir? Shall you continue?
Okay. So if we have this voltage source converter, maybe 3 leg, maybe 4 leg, maybe 6 leg power there. If 6 leg means 3 single phase system is there. Here we have a 3 leg converter. Okay. If we are going to maintain DC link voltage, VDC, voltage capacitor, how much? More than peak value of line to line voltage. Line to line means between AB, BC and CA. Between that, whatever voltage are coming, line voltage. If we are going to maintain this voltage, DC link voltage, more than peak value of line voltage. From that point, this voltage source converter going to work as a compensator. Means just crossing the peak value of line voltage. Thus crossing the DC bus voltage more than peak value of line voltage. From that point, this converter is going to work as a voltage source converter. This converter going to work as a compensator, voltage source converter going to work as a voltage source converter. Okay. Then point is how we can maintain. Clear na? How much DC link we should maintain? We should maintain DC link at least peak value of line to line voltage. Simple in one line. After that, After that, after we need to design inductors, means convert leg A, leg B, leg C. These are connected to phase A, phase B, phase C through the inductor. This inductor is responsible to flow of the power from line to converter side or converter to line side. Anyway, power is going to flow. Maybe converter to line, maybe line to converter. If voltage, line voltage more than converter voltage, then converter means power is going to flow line to converter side. If converter voltage is more than line voltage, then power is going to flow from converter to line side. Okay. Next point. Next point is how we can design these inductors. Okay. Next point is how we can design these inductors. So for designing the inductor, I will tell formula. Okay. Then next is also we need one ripple filter, one RC filter. The role of this one is, the role of this RC filter is to provide low impedance path, after, means you can say to provide low impedance path at higher frequency. This is more correct. But after half of the switching frequency, this filter is more effective. Simply you can say that if a value of C is going to value of frequency is going to increase. 1 by xc means x equal to how much? 2 pi f. F is going to increase means value of xc is going to decrease. So finally you are going to observe one low impedance path, and that path is useful to flow the whatever switching noise are there in supply voltage. Whatever switching noise you have observed in supply voltage. Again, always we are telling we are going to compensate the distortion. Distortion you can say. But in actual practice, one more conclusion is there. If again you can see very careful. Suppose in supply voltage and current, before compensation, how much distortion? In voltage may be 4%, current may be 21%. Assume that. Without any filter, supply voltage distortion how much? 4%. Current how much? 21%. After compensation, after connecting this converter, you are going to observe supply voltage distortion near to 21. We have 22, 20.5, 20, some value near. Supply can distortion how much? Near to 4 means 3.9, 3.5, 4.5. That depends upon other parameters. So means what type of conclusion we will get? Means using this filter, just we have shifted the harmonic from current to voltage. That is also one conclusion. Always we are telling that we have compensated harmony. But at another side also people have done some another conclusion also. But what is that conclusion? Conclusion is we have not compensated, just we have shifted only. If we are going to see whatever data I have told, before compensation 4% voltage, 21 in current. After compensation 21 in voltage, 3.9 4% in 21 in voltage and 4% in current. Just we have shifted distortion of current to voltage. And after using RC filter, whatever noise or whatever voltage noise are there, that noise you can put in ground through the low pass impedance. Pass. Okay. This is a second conclusion. This is also one very good conclusion. Means always in all the books they are telling we are going to compensate. But second conclusion is we have not compensated, we have shifted only. After shifting, voltage harmony you can separate out, you can remove from RC filters. Okay. Again, to turn on the IGBT, we need to use control circuit. The control circuit, whatever signal from PQ3 is there, that we will discuss. Again, that control circuit also need some input parameters. So we can use here what are the sense parameter? Voltage you can take, current you can take, supply, and also you can sense supply current, load current, DC link. These are our sense parameter. You can sense by sensor. Or in MATLAB you can sense by voltmeter, ammeter. Then this is one design. How we can design voltage source converter? The simple thing is there. In this case, first you can identify the value of how much reactive power you want to compensate. Or if you have multiple problem, you can find out the rating of the highest rating of rating of the converter to compensate highest disturbance. You can say require rating of converter to compensate highest distortion, highest problems, highest disturbance. You can see. In this case, suppose we have a reactive power, how many problem na? And it is 35 multiplied into 0.8. You are going to get 21. 15% extra you can take. You are going to get the 25 kVA. By 25 kVA, 10% extra we have taken. Okay, so you are going to compensate only reactive power problem. If reactive power, how many both are coming together, then we can make the calculation based on that one only. How we can do a DC link? Initially, I have told you you can maintain DC link voltage more than rated voltage peak value of line voltage, but you should maintain by this formula for sufficient operation. For sufficient operation, you can say. If we are going to maintain this much voltage, our converter is going to work fully as a capacitor. 2 √2 V line to line divided by √3 MA. Okay. And what about that capacitor voltage? Just you can use 1/2 CV square equal to 1/2 CV square equal to 3 phase power 3 VI. Then also you can put some overloading factor. Also you can put recovery time. Also you can put due dynamics, how much energy is going to change. 100% energy we are not able to change. Not change fluctuation, you can see. Due dynamics, how much due dynamics level of energy fluctuation, you can see. During dynamics level of energy fluctuation. Here alpha is the overloading factor. Then you can take 20% extra. K is the fluctuation of energy during dynamics. You can take 5 to 10%. T is the during disturbance, how much time is required to recover the DC link. Due dynamics, time required for recovery of the DC link. So generally we are going to take 300 to 500 microseconds. This is the recovery time, you can see. Now based on this data, we can calculate DC link. Here we have got 4832, some value we have got. Data, the random data we have put. Also you can put according to your requirement, your design. Also we can design DC link based on this DC side formula. What is the formula? CDC equal to how much? DC side current divided by 2 omega and ripple component on the DC bus. How much ripple component you are going to allow? So suppose you are going to allow, always we want perfect DC now. We don't want 10%, 20% ripple. Okay. So suppose we are going to allow 0.1 to 0.5 to 1% distortion only on the distortion or ripple on the DC bus. So 700 volt DC link is there na, 5 volt you can take. So based on this one also you can put. ID how much? 25 kVA converter are there, 700 DC link is there, 35 divided by 2 into 2 pi up into means 2 pi into 50 into 2 pi 2 into 2 pi into 50 into 5. So based on that one you will get the value of C. Inductor also you can design. Inductor you can design based on the whatever formula they have given. So ELF equal to how much? √3 GMA VDC 12 alpha FS ICR PP. root 3, okay. You see modulation index, the DC bus voltage divided by 12, alpha is the overloading factor, 10%, 50%, whatever you want, you can take. F is the switching frequency, maybe 10 kHz, 5 kHz, 2 kHz, depend upon your choice. ICPR means how much percentage of distortion you are going to allow on the compensating current. Means ICPR is the current refill of the 10% of voltage. Okay, means percentage refill on the compensating current. So refill on, don't tell, you can say harmonic frequency. Suppose you are going to allow 10% distortion on the compensating current. 10% distortion on the compensating current. That you can 10 by 20. Generally, people are going to take 10 to 25%. Yeah. Okay. Again, if value of the generator is so high, then current is going to saturate also. That is also problem. And if very less, then we are not able to get compensate very effective way. Then you can also tune value of this inductor during running. Okay. Next is how we can select value of RC filter. Simply whatever I have told now, you can create one parallel RC filter, see the impedance at fundamental frequency, and see the impedance at higher frequency. Continuously, this one is going to reduce the impedance. It means generally how we can connect, it is considered as R into CS very less than T by S, T by 10. So now based on that, you can convert the value of R, that total impedance. Okay. How we can say IGBT current and voltage rating? You can say descending voltage plus how much percentage of overshoot. So 700 plus 10% you have, if you have taken, so 770 you can take. But again, depend upon the market also. Maybe you can take 400. Maybe again I will tell cost of maybe 800 volt IGBT and maybe 1000 volt IGBT nearby only. In that case, maybe you can take 8000 volt. Also, maybe we will not get the 800 volt IGBT also. In that case, round figure rating you can take. Maybe 1000, maybe 1200, depend upon their design. And again, current rating, how we can decide? Current rating of the switch. Again, current rating of the I switch. I switch you can get based on the 1.25 ISP plus ICR. So means peak value of supply current. You can see peak value of the statecom current plus current plus value of allowed ripple current. That you can put, you can see. Here in practical purpose, we have taken 1200 volt, 200 ampere IGBT. Because we will not get 70 by 80 ampere. So maybe you can take somewhat higher side. This is the one simple control. In this case, what we have done, we have changed the voltage. Also, we have changed the DC link, and we have regulated the error between sense value and actual value, required value. For that, we need to tune the value of KPKI. Then output of that one you can consider as a signal. If other component are in terms of power, you can consider that one in power. If other component in terms of current, you can consider as a current. Means finally we can say that is signal only. We cannot say current and voltage. Then you can find out the individual phase power, PLA, PLB, PLC. Then you can make whatever formulation they have given. Standard book you can use. In that book they have given PQ theory. Based on that one you can find a value of PLA, PLB, PLC. Then inside of this one we have oscillating component. Those components you can do by LPF filter. And then you have one average value of PLDA, PLDB, and PLDC. Since we have all three phases, then find an average. If we are not going to do average now, then we are not going to get the load balancing phenomena. We are going to get a load balancing phenomena due to 1 by 3 only. If people are not going to use 1 by 3 now, then we are going to compensate reactive power, harmonic, and neutral current 4-wire system is there. But if you have 3-wire system, only you are going to see. If you don't want that unbalancing problem, you don't want to remove the unbalancing problem, then don't put 1 by 3. Okay, but now people have designed good for all 4 purposes. You can say like that. Okay. Then after you have got a PLA. The PLA, other PDC, both you can add. Finally, you have PT. Okay, total power. Similarly, you can find out reactive power also. In case of PFC mode, again one main thing. In case of PFC mode, only you want upper loop only. You don't want lower loop. In case of PFC mode, only you want to use upper loop only. Don't use lower loop. Low loop means AC bus loop. If you want to compensate voltage also, compensate voltage means you want to maintain rated voltage or some required voltage at PCC lines, PCC point. In that time, you can set according to your requirement how much voltage you want to maintain. You can put VT. Based on that one, VT star. Then regulate the PI, regulate the error. Then you can have a QQC. Then you add with QLA, finally QT you have. Then after that, you can calculate value of IAP, IBP, ICP. IAQ, BQ and CQ. Both you can add. After adding you have ISA star, ISB star, ISC star. Okay, some basic only. These are the formulas you can see how we can. This you can use Akage book or maybe any power quality book you can use. In that they have given these things. Okay. Then again main point are there. Why we want to add this to this? Generally, output of PI going to act as a output of DC bus PI going to act as a last component of voltage source converter. Again, main thing. Output of DC bus PI going to act as a last component of voltage source converter. So simply you can last component you can add. Again, below loop, AC bus loop, whatever reactive component you are getting from PI loop, that one, from that one, you can subtract the load reactive component. After adding also system will work no problem. But your KPKI will increase. If you have put both plus, but generally more correct way you can say QCC minus QLA. QQC minus QLA. This is more correct. Plus also will work no problem. But in the above loop na PDC minus PT that will not work. PDC minus PLA will not work. In that case, always we need to add PDC plus PLA. But in below loop, minus will also work, plus will also work. Okay. These you can see what are formulas I told. Now, how we can compute value of ISA, ISB, ISC star. See how we can calculate. Just you can see 1-2 minutes. Then I will tell. ISA, ISB, ISC. This is a standard formula only. VA divided by V alpha A, V beta B, beta A. For phase A, phase B alpha A, beta B, alpha C, beta C. For individual phases, we have final value of ISA, ISB, ISC. Okay. Then below that one, you can put alpha square plus beta square. For phase A, alpha square plus beta square for phase A only. The PT you can multiply, second case QT you can multiply. Finally, you have a ISA, ISB, ISC. Okay. The whatever thing I want to tell, that is the compensation based on the indirect current control. In that case, we need to compare with ISA and ISA star and ISA. Always we are telling reference is always positive only. So ISA star minus ISA, ISB star minus ISB, ISC star minus ISC. You will get error. That error again you can amplify. Whatever error you are getting, that one we can amplify. After amplification, you can compare with carrier based signal. Any frequency, 10 kilohertz, 2 kilohertz, 5 kilohertz of the triangular wave, sawtooth, triangular wave generally we are telling. Okay. So based on the triangular wave, you can compare. Okay, after comparing, what we will get? Suppose we have compared. Okay, after comparing, we will get gauge signal. Whatever gauge signal is coming, at that signal you can give respective phase upper IGBT. Okay, a same gauge signal you can pass through NOT logic. After passing through NOT logic, whatever signal is coming, that signal you can give associated leg lower IGBT. Clear now? Error, compare this triangular wave, gauge signal, due to respective phase, leg upper IGBT. Same gauge signal you can pass through NOT logic. You can give associated leg lower IGBT. This is the main thing. These are, you can say, maybe simulation results with some data we have given. 0.7, 0.07. ILS is 2 millihenry. Inductor you can say 3 phase bridge connected full bridge rectifier. Some value you can take RC filter, capacitor, then implementation also. Now you can see. Now you can see in this case what we will see? In this case, we are going to see simulation result for PFC mode. Okay. In PFC mode means to see the response, you can see supply PCC voltage, current and load current. The load current how much? Here level of load current is 27 ampere. Whatever rectification, after rectification, whatever DC you want to maintain, you can maintain and see the in supply side current before compensation. You are going to see 28% plus. Since we have a 4-wire system, in case of 4-wire system, we have a 3 single phase circuit. In that case, we are going to have at least maximum you are going to get are 48%. But due to source impedance, this one is going to decrease up to 40%. Okay. After compensation, you can see supply side current how much? Supply side current is 28, distortion 3.8. Why this one increased? Due to some losses somewhere, or maybe due to LPF, maybe LPF are not proper. After that, you can see value of supply voltage distortion near to 5%. This is our requirement. Always we can maintain this value based on the IEEE 519 and in 2014 or maybe 1991 anyone can put. In ZVR mode you can see what difference you are going to observe? 337. This is phase peak value. Here after compensation you are going to increase value near to 415. Our requirement 415. This is the 415 divided. This is the 415 divided by root 3 into root 2. This is 339.5. After compensation in ZVR mode also you can see na supply voltage and that supply current distortion and supply current and load current distortion are under limit only. And load current how much? 40%. Supply current become to near less than 5%. Again you can see how we can make a difference. Here 27 ampere current is there, 28. But in this case we need more current to regulate the voltage. Here 29.07 I got. Okay. In that way we can see our result is correct or not. Then you can see between supply current and supply voltage, what is the angle? Between supply current and supply voltage, both are phase quantity only. So both are near to unity base. Here not unity, some difference is there. Very small difference you can see. But in this first case, you are going to have somewhat unity base. Next point is Next point is, you can see here, this is the demonstration of the waveforms during PFC mode. You can see after compensation how much we have, less than 5% distortion. But main objective is what we want to see, distortion, also neutral current you can see. P and Q you can see. In these two figures, one is the load neutral, second one is supply transformer neutral. Both are equal and opposite. If both are equal and opposite, then you are going to see supply can near to zero. Supply neutral can near to zero, not supply can. Supply neutral can near to zero. At same time, you can see level of PCC voltage. Initially, we have assumed that our supply PCC voltage 160 volt. They have down up to 152. That in ZPR mode, this one we want to maintain 160. What do you mean of load unbalancing? You can see our load is unbalanced. See here. Phase A, phase C, phase C. Phase A, phase B, phase C. But in phase C, we don't have any load. In phase C, we don't have any load. Then, after some time, if more unbalancing are there, wave system is going to damage also. Some part of that one may also going to burn also. But due to this circuit, due to this this system, you are able to maintain all three phases supply can near to balance value only. You can see phase A, phase B, phase C. All three phase current are near to 4.5 only. Some difference are there because we don't have a balance voltage also. And also you can see what the nature of supply currents. Compensating current you can see all three phases. And also you can see dynamic condition. During whatever we are going to put dynamic, during dynamic we can see supply current, load current, DC bus, AC bus, how they are going to change. What is behavior of that? Those you can record from DSO. Now you can see. This is ZPR mode. In PFC mode, what we have done? In PFC mode, our voltage has reduced up to 152. But we have taken a no load 160 only. So we are able to maintain 160. After compensation, here you can see always we have a leading power factor. See figure number J, 1.83 kVAR leading. This much power we want to compensate the voltage 152 to 160. 8 volt grid voltage we have compensated. 8 volt grid. Okay. And other is okay. So we have compensated supply voltage up to rated value with less than 5% distortion. That I also want to tell. Plus less than 5% distortion. Okay. In supply side, also neutral current free supply neutral. Neutral current free supply neutral. Then also after that you can see we are the dynamics. Dynamics always we can see during load change, during behavior change, how VT and VDC is going to change. Okay. So for hardware implementation, whatever I have told now, that one you can use any processor. Maybe you can use microprocessor, you can use microcontroller, DSP, whatever expertise you have. Any type of converter you can, any type of processor you can use, but you need ADC and DAC. Based on ADC, DAC, you can design their sensing or power conditioning circuit. Means, see what type of quantity we want to sense. So, print out नहीं ले लो जल्दी प्रोजेक्ट बना लो जल्दी बस को जल्दी के पास रखा ना एक
एक तो वो बंद करा
क्या बंद कर कंप्यूटर
तो कुछ लिखा नहीं कि प्रोग्राम चल रहा है इसका नहीं
आपका कुछ नहीं चला रहा होगा टाइम पास Okay, then we have a digital I/O. So you can see this is the picture of the processor. You can see means whatever processor are there, na. So processor you can select based on the your requirement. How many sensing element you want, how many quantity you want to sense. Based on that one, you can decide ADC. Second one, also you can decide processor speed. Suppose you want to do some research work, you want to do some means what we can say, develop some new thing. In that case, you should have some high-end processor, so that we can process some new thing also. No? Otherwise, we can process an old thing only, PQ theory, always we can SRM theory, then we don't have anything new. If we are going to use low cost processor, no, we can use the power. But for commercial application, that is useful. But for research application, we need to develop some new thing. For develop new thing, we need some more high-end or maybe high-speed processor. In that place where we are going to parallel processing, not sequential processing. All the microcontroller, they have a sequential processing only. Sequence by sequence, they are going to process. For field application, for commercial application, that is useful. But in case of research application, we need high-end processor so that we can develop some new theory and new thing also. Okay. So we are able to process, or we are able to do some complex calculation also with gain tuning or with those things. So for that one, we need some high-end processors. These are the channel sensor. You can design the sensor. Maybe also you can purchase the sensor in the market, LEM25, LV25, ABB sensor. Then based on processor requirement, you can design. Based on the processor requirement, not based on your requirement or my requirement. But whatever processor you want, you have a bidirectional ADC or maybe unidirectional ADC. Na, based on that one, you can design. Okay. And also you can see the inverter. If you have inverter, we don't have any dead band circuit, or if you don't have anything, na, in that case you can develop the dead band circuit. Otherwise, if during transition from one to second phase, na, your DC link, your IGBT going to short circuit from DC link. Or not IGBT, DC link going to short circuit from IGBT. Because during transition, na, whole leg going to work as a short circuit. So for that one, we need to design some dead band circuit. You can maintain that dead band how much? Near to 2 to 5 microseconds, not more than that. So we have designed dead band based on this NAND gate, IC7400. IC7400. Okay. See here, and try to maintain incoming and outgoing. Try to maintain delay between incoming and outgoing pulses, and to say the DC from short circuit. Suppose we have a very low cost processor only, low cost converter, 5,000, 2,000, 3,000, 6 IGBT only with driver circuit. So in that case, you can use this thing. Okay, because we don't have so much money. In that case, also you can use low cost processor, low cost converter you can use, but processor we need high end. Okay, these are RC filter. Whatever RC filter I have told, that one is going to provide path for switching noise. So this one you can use. Okay, this is one thing, something I have told regarding how we can design the system. Next one, suppose we want to apply this thing in wind-based energy system. So this is what basic theory. I will tell how we can use this one. In this case, suppose we have 3-phase induction generator. Maybe synchronous generator also we can use. Maybe any type of generator you can do, no problem. But our input is wind maybe. So wind is always going to fluctuate. How wind is going to fluctuate? That depends upon the wind velocity. Sometimes wind is maybe 10 millimeter per second, maybe 10.1 meter per second, 9.9 meter per second. Some small change is there. For that one, due to that one, power also going to fluctuate. To store that power, to use that power, we need to provide path. For that one, we can, in place of DC link, you can use battery. In place of DC link, we can use battery, and whole system you can design. Again, in this case, problem are somewhat different, you can see. In this case, major problem are voltage and frequency along with harmonic, reactive power, unbalancing, neutral current. Those problems are there because what we can say, it's just we have changed the supply only. In that case, this whole converter is going to work as a power quality conditioner, as well as this one is going to maintain voltage and frequency at rated value. Okay, this one is going to maintain voltage and frequency at rated value. How much rated? Whatever you have put 415, 230, 110, depend upon the conditions. Okay. Now what we can do here? You have used what we have used. Here, assume that we have three systems: turbine, generator, load. Assume that all three have same torque. No problem. Our system is going to run smoothly. If turbine and this one generator have somewhat nearby torque, and we have some constant rated voltage, assume that. Suppose small variation also there. There is a small variation going to take care by the battery. Okay. If load demand is going to decrease from rated value, load demand is going to decrease maybe 10%, 20%, 30%, or 40%. In that case, our voltage is going to up, voltage is going to increase, and voltage frequency is going to increase. Up to how much? Maybe that depends upon the how much power had decreased. Voltage frequency is going to increase. 10%, 20% means voltage frequency power you are going to observe if your load demand is going to decrease. Second case, if load demand is going to increase now, then our frequency also going to dip and voltage also going to dip. This problem you want to solve by this voltage converter. Again, if load demand is going to decrease, then whatever extra power then that extra power you can store the battery. That is advantage. If load demand is going to increase, whatever store power you have, that power you can use as active power support to the load. This type of features we can see. This setup we have in our laboratory. Somebody, one person also work in that area. As a PhD means as PhD degree. So we have developed this setup with generator. If somebody want to work, then that can also work in our college. In this whatever system I have told, DVR, distate com, DVR, distate com, and that TPC regions. Battery charging also, solar power converters, induction motor drive, these areas also. Okay, this one you can see. You have seen this equation GQ the way, electric drives. Just using those equations, we have developed this system. No problem. Okay, here you can see again in more character you can say TM, T, TL are the mechanical torque, load torque, electrical torque. Okay, then if you have some disturbance here, then you are going to see voltage frequency problem. Okay. In that case, also we need to develop some control circuit for this converter. So for that one, maybe you can use single phase PPK or maybe SR you can use. It is not a problem. Here we have SR. By SR, we generate the required reference current. Okay. Require reference current. And frequency, in place of DC link loop, here we have used frequency link. This much change we have done. Other are similar. Then also we need to design transformers. How we can design transformers? For that one, whatever you are knowing, theory from that third semester, whatever we are teaching machine theory, transformer, based on that theory, we can design the KV rating of transformer. After knowing the supply current and neutral current, load neutral current and transformer current. Okay. Now we can see we can develop some control. So we can see how we can develop these setups. Here. How we can develop that neutral current compensation techniques. Here you can see we have one multi-variant transformer. Based on that one, this is this thing, load, rectifiers. Here we have a generator inside of this table. Then we have that one we are going to apply as a wind farm. Then we have compulsory that neutral kinds. As you can see, load neutral, supply neutral, this equal and opposite that we want to see. Okay. So you can see many connections we can do. Delta star, double delta, zigzag double delta, fog connection, those we can do. And we can find out some conclusion. Okay, these algorithms I am not telling. Whatever SRF say the same thing we can apply. These are some research work only. Now we can see how we can set up the develop, how we can develop the setup of that DVR, that wind farm. Here we have developed. This is our generator. Whatever generator I have to show before that also. So this we have two induction motor coupled. So one motor work as a turbine, second motor work as a generator. After that, we are going to take power in this switch, and we have connected one that KVR requirement. And after the boosting that residual voltage, a particular level, required level, that one we are going to supply these loads. These are load, rectifier, then R load, then this is the inductors. Using this VFD connected to supply source. Output VFD connected to this generator. And by this node, we have changed the frequency 50 to 48, 48 to 52. Means plus minus 3 hertz we have changed. And we have maintained near to 50 hertz our supply frequency. This side we have put battery and those things. The converter, those things you can say. These are our sensing element. You can see. Since these are inverters. These are our isolation and deadband circuit. Make the isolation power circuit and control circuit, we need this circuit also. To put the isolation between power circuit and control circuit. In that way we can develop circuit. What I have told now, first you can take the processor, see the speed, see the requirement. After that you can, based on the ADC of the processor, you can develop this PCB by your own only. Because if we are going to purchase somewhere, then they will give their design only. If we are going to change the design, they will take more cost. Those things we want to remove. Okay, now this is our deadband circuit. We have texture here. And we have created deadband 2.5 microsecond. Okay. Now if you have some question, you can tell me. Because time is near to 2:30. And some other lecture also will start. Okay, if somebody want to work in the area of that maybe solar, wind, district from DVR, or maybe UBQC, so they can come in our college, they can work.
Okay.
We will give some of the guidance also.
Yes, sir. One question from the participants. It is just in our screen.
Hello?
Yes, it is just in our screen. One question from the participant.
Where?
In our screen. Sir, it is visible in our screen.
How can calculate the interface inductor in the can refill more than 10%? Okay, 10% means suppose we have a G-state comp can suppose 10 ampere. So 10 ampere means 10 into 0.1, whatever value will come, that one you can put as a ICRPP. Okay, if 25 ampere, if 25%, so 10 into 0.25, whatever value will come, that one you can put as a ICRPP. Okay. Means if more than 10%, so just you can multiply whatever the state come can talk, that one into 0.1 or 0.2, 0.5, whatever value are there. Okay?
Yeah. Okay, I think participant is there, so is okay.
Any other question?
So right now, no more questions.
Hello?
Okay, fine. Nikun sir is also with us. Okay, Arya sir, you can on your video for the screen.
Okay.
So, hello, Arya sir.
हाँ.
First of all, sir, thank you very much for accept our invitation and spend your valuable time with us. Sir, you have nicely explained the D-Statecom and its application in wind-based DC systems, and you also incorporate the many issues which are really create the problems when we go for the research. And I am really proud to feel that you have give the open invitations to our all participant if they want to do some further research in this area. Then SVNIT is always supported. So thank you very much, sir, once again. And such kind of knowledge sharing is maybe possible continue in nearest future also. Thank you, sir. Thank you.
Thank you, sir.